Discuss. Okay. So today we're gonna discuss the Doppler effect of waves, and we're gonna show you some mechanism for what the Doppler effect is. The definition of Doppler effect is that whenever the source of any wave and the observer of that wave are in relative motion, Relative motion means the distance between the source and the observer is somehow changing over time. It might as well be that the source is moving, observer is stationary. It might as well be that the observer is stationary and the source is moving. It can happen either way. But the required logic is there should be some relative velocity between the source of a wave and the observer of that wave. If it so happens, then the observer does not receive the actual frequency or original frequency of the source. He perceives a somewhat different frequency than the source's actual frequency. So I'll say this again, that because of the relative speed between the source and observer, an observer observes a different frequency than the actual frequency of the source. So this change of frequency, this incident of observing a different frequency, is what is called Doppler effect. So the way this can be explained is that a very common example, let's say you are standing on the rail station, rail engine is coming by while blowing its horn. Is gonna, let's assume it's gonna blow horn for a pretty long duration. As long as the source is coming towards you, first stationary on the platform, which is the most easy example for us to comprehend or visualize. When the source is coming towards you, you're gonna hear a higher frequency of the sound. Why? I'll show this to you. And when the source is gonna leave from you, you are going to hear the sound at a much lower frequency. The reason is actually quite simple. Here they have made two different effects with two different scenarios. So I'm going to explain this to information over here. Here, let me zoom in. Where is this? আচ্ছা এই 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 ইকুয়েশনের ডেসক্রিপশনটাতে একটু ভেজাল আছে. Here they are saying this speed of sound, the speed of sound. It's actually slightly wrong. I did not actually look it up properly. So you might actually have to do some correction in your booklet, because already booklet print করে বানাই দিয়ে দিয়েছে, আমি এটাকে খেয়াল করি নাই. আচ্ছা আমি এই জিনিসটা বুঝাচ্ছি ডপলার এফেক্টটা কেন হয়. Let me try and pull up some animation if I may. Let's see if we can make some simulation. Okay, beautiful simulation. So let's try to understand what is actually happening for this thing. Currently, this source is positioned here, or maybe I can place it over here. And let's say the observer is, I'm placing Can I place a different observer? No. Acha. ব্যাপার না। Let's say this is the source and this is the observer. Currently the frequency of the source is 100 hertz. This is the f naught is the f naught is the observed frequency, f observer observed, and f is the true frequency of the source. True frequency means this is the actual frequency. So this source is not essentially 100 hertz. This is just a number that, and the animation is working to make sense to us. So it is emitting 100 pulses of sound. 100 pulses of sound means 100 complete oscillations every second. And when the observer is stationary, there is no relative motion between them. He is gonna also experience 100 pulses of sound passing through him. So as long as there is no relative velocity between the source and the observer, they will hear the sound exactly the same frequency. So in this case, the observer will observe the exact same frequency, 100 hertz. Now, if it so happens that the observer starts to slowly move towards the the source slowly starts to move towards the observer. So let's say if we increase this one, you see this is the shape that the source starts to make. The reason we have a shape variation like this is because, let's say it made the first source over here, then one time period passed by, and because it is moving, the second sound was produced slightly on the right side. The third wave was made slightly on the right side. The fourth wave was made slightly on the right side. So it's making the crests or the waves, but as it is making the waves, it is slow also moving to the right. So the center of all of these circles are not concentric right now. They are all swashed a little bit to the right. This makes the gap between the individual crests smaller on the front side, and the gap between the wavefronts over here larger on the back side, which means if your observer is placed over here, he's going to experience a much higher frequency. You can see over here, because I gave a little bit of speed over here, there is a calculation for this. How do we get this number? I'm going to show you the calculation. Currently, I'm just trying to show you that why that happens. There is a physical reason that this is happening. So in this case, this person is going to uh, experience a much higher frequency compared to the source's original frequency, because sound waves are going to pass through him at a higher rate, because you can see it very well that it is the same medium. This is, let's say this whole thing is air medium. This is a sound source. This is the observer. So the speed of air V is constant throughout because it's the same medium. But whenever you have smaller lambda, you will definitely have higher frequency, which is we can see over here. And here, because the lambda is bigger, the observed frequency will be smaller, which means if we just place the observer right on the back side, you can, I mean, let's say we place the observer over here, and you see, as long as the source is coming, observer is experiencing a higher frequency sound. Now the source is going to pass him by. So now he will be remaining on the on the hind side, on the behind portion of the source's motion. And you'll see now he is going to start to observe a much smaller frequency. You see, even till now it is 200 hertz, and if we allow it, you see it has changed suddenly to 67 hertz. Why is that? Because you can see, as the source is now moving away from him, he is experiencing the sound waves at a much bigger delay, because each sound is made a bit farther away from him. So that sound is taking a bit longer to reach to him compared to exactly one time period. The source is making the sounds exactly one time period after, which means 0.01 second after. But each of these red circle wave is taking more than 0.01 second to reach him, because they have to cover that extra distance that the source is moving by to reach up to him. That's why now his observed frequency is becoming smaller. This is a very interesting observation, which can lead up to astronomical case even. So what I'm trying to show you over here is that whenever, for this example, when the observer is stationary and the source is moving, what I'm trying to show you that whenever the distance between them is decreasing, the observed frequency will be higher. Whenever the distance between them is increasing, the observed frequency will be lower. That's the first thing that I would like you kids to appreciate.
স্যার, যখন সোর্সটা অবজেক্টের দিকে মুভ করবে তখন কি ফ্রিকোয়েন্সি স্পিডটা মানে কমতে বাড়তেই থাকবে নাকি একটা কনস্ট্যান্ট ভ্যালুতে থাকবে?
Beautiful question. This would depend upon the relative velocity. Let's say if the source is, in this case, we are assuming that the source is moving at a constant speed. So it is not continuously accelerating. If it so happens that the source is continuously accelerating, then we'll see a gradual increase of speed. For when the source is placed, uh, when the source is on the left side, if it is keep on accelerating, then these waves are gonna keep on getting squashed. So there'll be more smaller, even smaller wavelength. So how much of a frequency deviation the original frequency and the observed frequency is gonna have is dependent upon the instantaneous relative velocity of those two things. Instantaneous relative velocity of those two things. So if the relative velocity over time does not change, for example, the example over here, the observer is the source is moving at a constant speed. That's why you have equal gaps over here. But if the observer was actually making okay, in this case I cannot do this because if I increase the source velocity, the animation simply starts again. Okay, this is actually pretty interesting. Here they have given the animation as 1.3. Achha, before I show you this part, I would like to ask, মানে এই basic behavior within one, এই গ্রাফটার মিনিং বুঝা গেছে কিনা, যে কেন আমাদের হায়ার ফ্রিকোয়েন্সি অবজার্ভ হচ্ছে আর কেন পিছনে চলে গেলে লোয়ার ফ্রিকোয়েন্সি অবজার্ভ হচ্ছে, এই ইনসিডেন্টটা বুঝা গেছে কিনা সবার?
স্যার, সোর্সের ভেলোসিটি যখন বাড়িয়ে দেন তখন অবজারভারের ফ্রিকোয়েন্সি নেগেটিভ হয়ে যায় কেন?
আচ্ছা, ওই অবজার্ভার ফ্রিকোয়েন্সি নেগেটিভ হওয়ার কারণ আছে, সেটা আমি বলতেছি। There was a certain part where the observer frequency এখানে একটা জিনিস খেয়াল করো, here it is one thing, the source velocity in units of speed of sound. So this one represents currently the source is moving at 70% speed of sound within of air. So we have a certain observed frequency that is higher, and when the source is passing through the observer, he's experiencing a lower frequency. So what this thing tells us, for example, mone koro, let me give you a simple example. Let's say here comes the train engine. Forget about the whole train because the whole train is going to make more sound with the friction and everything. Here comes the train engine blowing its whistle. And let's assume that there is no other sound other than the whistle for the sake of simple understanding. The driver who is driving the train, the whistle mechanism of the train and that driver is moving at the same velocity because they are in between. This is not changing over time. So the driver of the train is going to, the driver of the engine is going to hear the exact same frequency that the source is making. Both of them are moving in the same direction simultaneously with respect to the surrounding. So the driver will get the exact frequency of the siren because he is moving at the same speed. Now, the person who is standing on the platform, as long as the engine gets closer to him, he is going to experience an increased frequency than the original frequency. This will keep on happening till the source comes to his closest. The moment the source or the engine will get past him, which means whenever the distance closing in is finished and distance increase gets started, then the whole frequency is gonna start increase. Sorry, then the frequency of the frequency is gonna start decrease, and that will maintain for the entire living part. So in true sense, the sound that the person gonna hear is something like this. First, a high frequency, like that, really high frequency. I cannot go very high scale in my voice. And then as the sound drops by, then it's gonna be blunt, like so it goes like that. But other than experiencing the frequency, he's obviously going to experience another happening, which our brain takes to be the more prominent effect, is that whenever the source is going to come by, the intensity of the sound will also increase because now the source is closer to the observer. So the volume of the sound will also increase, and as the source will leave from the person, the volume of the sound will also decrease. So this is definitely going to happen. The volume increase and volume decrease is depending upon the a relative distance between the source and the observer, because I proportional to 1 by distance squared, which we have seen in our earlier theoretical classes. So this is one happening is that the change of the intensity or the volume, how much loud is the sound going to appear to your ear. That's definitely one factor. The other factor, which is the more important factor that we're discussing over here, is the change of frequency. So if I try to give you a bit of visual for the frequency, for those who are using headphones, beware. This might actually be slightly, so this is a 50-second video, which is nice. So this is the person where the observer and the source are moving at the same speed. So you heard that sound. Try to remember that frequency. Did you hear a very distinctive difference? Once again. Did you hear a very distinctive difference as the car passed by? There is a did you sense the variation of sound?
Yes, sir.
Yes, sir.
That's basically Doppler effect. That there'll be a certain change as the source gets passed by us. So the same thing can be simulated by the other behavior as well. I'm going to show you what happened to the minus thing after a little while, but let me just continue for this part. The other thing that can happen is that we can keep the source stationary. For example, in this case, I'm going to keep the source exactly at the center and not going to move the source. So I'm going to keep the source stationary. Let's say I'm going to move the observer. Let's say in this case, the source is producing a frequency of perfectly 100 hertz. So I'm going to keep the source stationary, but I'm going to start moving the person. Now, what do I mean by this, moving the person? This is very simple. Let's say there is a police siren that is going by at a certain location, or there is a fire alarm that has gone by, and then a person is walking towards them. So if the observer is moving towards the source, or let's say if the observer is getting away from the source, that also can lead to a Doppler effect, which means there is a relative speed between the source and the observer. That's the basic part. It can happen either by the motion of the source, or it can also happen by the motion of the observer. Either one, or it can also happen work simultaneously. Simultaneously, don't worry about that. I'll go ahead and explain that for you. But the mechanism, the mechanism when the source was moving was that whenever the source is moving, in front of the source, the waves are getting squashed. Behind the source, the waves are getting expanded, resulting in the Doppler effect. That was the scenario. If the source is not moving, if the source is stationary and the observer is moving, then we're going to have something else. Have a look. If we now make the observer move towards the source, he is experiencing a higher frequency. Now, you might wonder, why is he experiencing a higher frequency? Now, let me explain this thing. If this observer was stationary at this position, then because the source is producing a frequency of 100 hertz, which I cannot change, which is good. If this person was stationary over here, he would essentially experience each crest of these red circles 0.01 second gap. It means he hears one sound, and then after 0.01 second, he hears another pulse. After 0.01 second, he hears another pulse. Our ear cannot distinguish that sound because our hearing and optical memories are both 0.1 second. So we're going to hear a continuous sound, but he is going to hear the frequency exactly 100 hertz. That is if this person was perfectly stationary. So the rate at which the source is producing sound, he would be hearing the sound at the exact same frequency. But now what is happening? This person is actually moving closer to the source, which means this person, as the waves are traveling towards him, he is also getting closer to the wave. So because of his own velocity, he is going to cross through the wave by a bit faster compared to if the waves only were crossing towards him. So if I give you a bit of an idea, let's say in this case we have given the speed of the person is 0.5. I have given negative because here he is moving to the left side of the source. So I'm trying to show you the closing in. So if he is moving half the speed of sound, which means his speed is half the speed of sound. So he is moving towards the source. So every single time, I mean, if I just do the step, for example, okay, so what I want you to understand is that I want you to visualize that between this gap, there is a time duration. Between this gap, there is a time duration of 0.01 second, the time period of the source from a frequency of 100 hertz. But whenever the person is going to move towards this part to this part, he is not going to take this whole part. I wish this graph was more workable with the grid. Speed of sound is actually 340 meters per second. That's why this is a bit different, I believe. Anyway, we'll try to work with it. So what I want you to see, that whenever the person is going to move forward, he is going to experiencing the sound in a much smaller distance. So have a look. Let me reset, pause in a certain position. All right, let's try to get this scenario. If the person was stationary, this wave would have to cover this much distance to reach to this person. Because now the person is getting closer to this thing, try to have a look that how far the person have to move before he actually gets the second wave. He doesn't have to move about 2/3 of this distance. This is about nearly 2/3. Assume this distance is 2/3 of the grid size. But if I just play it, have a look. He did not have to move 2/3 of the bus. He pretty much have to move like about, let's say, 1/3 or a bit more than 1/3 of the length to get the second wave. So he is going to experience the waves much sooner than 0.01 second, because now he is walking towards the source. So this scenario is slightly different from the first one. What was happening in the first one, when the source was moving, the actual shape of the wave was getting squashed. Now, because the source is not moving, the shape of the wave is remaining the same, but the person, by his own virtue of motion, he's experiencing increased number of waves because he's moving towards the source. And that if we allow it to follow through, this will keep on happening as long as the person is closing in. For example, this is the point of change. So I could pause it exactly at the perfect moment. Now, if I give it a bit of a step, now you can see the frequency has become smaller. Why? Let me show you. If you see now, there is no slow motion here, but I can do the step motion. You see, the person experiences one wave right now, and then he is moving forward, and this is where he experiences another wave. And he moves a lot more distance to experience another wave. So he is continuously moving at a constant speed, and he is now experiencing the waves with a much bigger delay because the waves have to catch up to him. The produced waves from the sound have to catch up to him to reach to him. So he's not going to get those individual sound waves, 0.01 seconds difference. The time each wave would require to reach up to him is going to be more than 0.01 second, because the waves have to cover the distance and also the additional distance within which the sound per person has gone forward. That is going to take some additional time. So which makes a relative drop of the observed frequency. So which makes the frequency f naught 50 hertz. These ideas are pretty simpler. If you don't want to understand this to its very, if you don't want to remember this to its very core, you can remember it by a very simple term. Closing in means frequency increase. Getting further means frequency decrease. These two sentences are going to help us to build up the formula a lot. I'm going to show you how the formula works. So remember this. Closing in means higher frequency. Getting further means lower frequency. So there are two different formula that applies, one for the sound wave that we observe, and the other one observes for the speed of light. Doppler effect is also observed for speed of light, which is a very interesting behavior, because particularly from the Doppler effect, we came to understand and observing the celestial constellation, we actually came to understand that the idea of ever expanding universe, the Hubble telescope that gave us this information, this actually came down from the idea of the Doppler effect. So I'm going to explain that part as well. But we have two different equations for that. Before I go into the equation, I'd like to show you the supersonic effect. But before I get into that, I'd like to ask anyone, এই পার্টটুকু বুঝা গেছে কিনা, এই অ্যানিমেশন আইডিয়াটা বুঝা গেছে কিনা, experience the wave at a faster rate or experiencing the waves at a slower rate, এই পার্টটা বুঝা গেছে কিনা?
যদি ডিসটেন্স 0 থাকে তাহলে ফ্রিকোয়েন্সি মানে কত হবে?
What do you mean distance 0?
মানে both are at the same point.
Oh, if both of them are at same point, they are not moving. He's going to experience the same frequency. For example, I can place the observer exactly at 0, and he is not moving. He's gonna, if there is no relative motion, no matter what, irrespective of his position, he's gonna experience the same frequency. If there is no relative motion between them, if they are not moving with respect to each other, the distance would not matter. The distance would, in that case, would simply cover the idea of volume. If you're closer, you're gonna hear a louder sound. If you're further, you're gonna hear a much dimmer sound. But you're gonna experience the same frequency whatsoever. So if the observer is far away from the source, he's gonna get a smaller amplitude of the wave. If the observer is closer to the source, he's gonna get a bigger amplitude of the wave. But for both of these cases, the observed shape of the wave or the frequency of the wave would be exactly same. Did I answer your question?
Yes, sir.
Acha. So এটা হচ্ছে এই সিনারিওটা. আচ্ছা, any other question about this?
Sir, moving bodies জন্য like either source or the person observing, যদি either move করে তাহলে effect কি for the same?
Yeah, we can achieve that as well. For example, let's say the source and the observer, if both of them are moving at the same speed, let's say, let me show you that. Let's say here is a source. So the source is gonna move at close let at let's say 0.3. I'm using a bit smaller speed. And observer is also gonna move at minus 0.3. Have a look. There is practically no difference. If both of them are moving at the same speed, then he's still gonna hear the same sound, same frequency, because they are not in relative motion. As long as the distance between them is not changing over time, he's gonna experience the exact same wave. So what is happening over here is that the squashing effect is not affecting his observation, because he is moving forward to compensate for the squashing effect. The person is practically moving forward for every single wave information, and the wave has to travel a bit more to reach up to him. So ultimately, the person is experiencing the exact same frequency. It can equally happen if the person is looking on the right side. For example, if I place the person somewhere on the right side. Oh no, sorry, I was trying to place him on the right side. Let's say the person is over here. In this case also, he's gonna observe the exact same frequency. If the source and the observer, they are moving simultaneously, or like I said, if they don't have any relative velocity with respect to each other, relative velocity means that the distance between them is not changing with respect to time. In that case, the observed frequency will be exactly the frequency of the source. If there is a variation of their velocity, if the distance between them is changing, which means either they're getting closer or they're getting farther away with respect to each other, then there will be the Doppler effect. Do I make sense? Fayaz,
না স্যার
বুঝে গেছে? তুমি কি কোশ্চেন আনসার পাইছো? Acha, there is a bit of a background noise from your channel, so I hope it made sense. Acha, I'm gonna now show you the additional part which one of your students asked, because in this animation I can, which is the idea for supersonic and subsonic speeds. Whenever anything, so let me reset everything in 0, let's say. Let's place the observer at 10 meter distance. Okay. The idea is that if a sound source moves at the speed of sound, this is the case that we call supersonic speed. It can be said to be a friction. So what I'm trying to tell you is this. Let's say in this case, the source is making circular waveforms or sound waves, which is slowly emitting out from the source and moving in all directions. The speed of these wavefronts is equal to the speed of sound, which is in dry air, 0 degrees Celsius, it's 334 meters per second. You don't have to know this value, but if you do, it's good. But
বলতে পারেন আমার সিগন্যালটা একটু ডিস্টার্ব করে দিই।
Faiz, I'm not hearing you right. Your voice is cutting off. Hello?
জাস্ট আরেকবার একটু বলতে পারেন স্যার, লাইক আমার একটা সিগন্যালটা সমস্যা করেছিল।
Acha, which part?
জাস্ট একটু আগে যেটা বলেছিলাম।
Acha, বলতেছি. So in this case, the waves are produced from the source at 100 hertz frequency, which means each of these red lines are going forward at the speed of sound. That's basically how we define speed of sound. Now, if we slowly start to increase the speed of the observer source, that's the source velocity, then these waves are going to get closer to each other. Here, the speed of sound is about, here I've said the observer the source speed is about 0.6 times or 60% of the speed of sound. If I slowly increase this thing, the closer I make it to the speed of sound, you see that more squash each of these things are making, because you have to understand that now I have given the source speed, source velocity in the units of the speed of sound is 0.9, which means currently the source is moving at 90% of the speed of sound, which means it makes the first wave. The first wave only is able to move a little bit, then he makes the second wave. So what this produces? It produces a huge amount of energy concentration in front of the source. And this is what we call the sonic barrier. Sonic barrier means whenever this thing is exactly at 1, then this thing is the actual representation of a sonic barrier. Sonic barrier means currently if the speed of the source and the speed of the sound perfectly matches, then every single sound that the source produces will not actually go in front of him. It will keep on traveling with him. So all the energies that he's going to emit as sound wave from his engine or from his devices or from his siren, they're going to keep traveling with him, which means all the compressions and rarefactions are going to get squashed within a very small space, very tight space. The actual physics of what happens in the sonic barrier for the physical medium is actually quite complicated. I'm not going to get into that, but what I'm about to tell you is that the total energy of the sound wave gets compressed within a very small space, and going through that energy barrier takes a significant amount of rugged structure for the aeroplane. So this is not very common for the regular planes, for example, like the commercial flight or airliner flights. This is more common for the fighter planes. So the fighter planes can move in a much wider range of velocities. Supersonic speed is the part whenever they actually go from the, I mean, if the speed of an object is a proper fraction of the speed of sound, we call this motion subsonic. And if it is equal to the thing, it's called supersonic. And if it is more than the speed of the sound, it's called hypersonic. At least that's what I know. I'll still look for it.
But sir, এই পয়েন্টে তো still frequency বা স্পিডের তো কোনো এমন ভ্যারিয়েশন হচ্ছে না, বা সব ওয়েভলেন্থ এটা তো কমতেই আছে।
আচ্ছা না, ভুল বলছি, my bad. This is the similar situation for Doppler effect. Sorry, hypersonic. ভুল বলছি। Hypersonic speeds are given for Mach number 5 and above. Mach number is the ratio for the object speed divided by the stationary fluid speed. So, never mind. You don't have to understand hypersonic and supersonic. The primary thing is that if the source is moving at a speed higher than the speed of sound, then it is going to continuously leave that produced sound behind itself. So let's say this source is producing a sound, and each of those crests are behind it, because if the source's speed is more than the speed of sound, so the moment it produces that sound, and it actually goes through that sound immediately, because that sound itself has a lower speed than the object, which means that sound is going to be left behind, and the source is going to go forward. I can actually increase the speed of the source even higher, and this can lead to a situation like this. The reason these frequencies are showing up to be negative hertz, because essentially what you need to understand, this value is actually an outcome of a mathematical calculation. The person can never hear a negative hertz. This person practically would not hear any sound, because as long as any of these sound waves or these wave circles don't reach up to him, he shouldn't be able to perceive the sound. But when the person will perceive the sound, he will hear a large wide of cracking, because whenever the person will hear this sound, let's say, I'm going to pause a little bit. If you have a look over here, this is about to finish, you'll see that these are the sound waves he's going to experience. So if this person is standing over here, he is going to experience this sound wave first, then this one, then this one, then this one. So he's actually hearing the recent sound first, and then the earlier sound later, because that's how the sounds are approaching towards him. So he's gonna hear a frequency like that. Now, the formula gives us a -100 hertz, because now the spacing of these waves would be exactly similar to the original wave gap. Have a look at this gap size, that from the first wave to the second to the third and the fourth for the receiver part, and this is the exact same amount of gap if this source was not moving at all. For example, if this source was not moving at all, the gaps would be exactly same, because this person is going to only experience a small part of the wave. He's not going to experience the whole circle of the wave. He's going to experience what part of the wave that passes through him, through his own location, through his ear. So that's why this was shown to be -100 hertz. The physical significance for this thing to become negative is to give an idea that this frequency that is being observed right here is within the supersonic range. So if it is within the supersonic range, we're getting a minus value. You don't have to bother about the supersonic part, because it's not a part of your syllabus. For your syllabus volume, you're only going to handle problems which is within the fraction of speed velocity for regular life experiences, not like fighter planes or other stuffs. But just because it is a very intriguing part and interesting part for this Doppler effect, I wanted to show you this part. So that's the animation part, and that's the explanation. And here comes the formula for the Doppler effect. I'm not going to use this formula. I'm going to use a version of my own, which I have used in my study periods, like it as well.
So fighter প্লেনরা কি সুপারসনিক স্পিডেই ট্রাভেল করে এক্স্যাক্টলি, নাকি বেশিও ট্রাভেল করতে পারে?
Well, whenever any fighter plane is in the hangar, or is about to start its journey from the runway, it is definitely stationary with respect to the atmosphere. It starts its journey, then it is subsonic, then it can speed up by burning its thrusters at a much higher fuel rate combustion, and then it can essentially reach to the slowly speed up to go through the supersonic or the hypersonic level. And how fast is it going to move? It depends upon the capabilities, structure integrity, engine design of this whole thing. So obviously they can travel at a lower speed, but it's not the lower speed that defines fighting superiority. It's the highest speed that actually defines that.
স্যার সুপারসনিকের যে ক্রেস্টার টপগুলো যে একসাথে কম্বাইন্ড হয়ে যায় তো তখন কি ডিস্ট্রাকটিভ ইন্টারফিয়ারেন্স হয় না?
No, it actually produces a small bit of cloud because of the atmospheric condensation. I was looking for my writing pad. Okay, I can actually show you another video for how does the sonic boom. Sonic boom is the large sound. I mean, if a device is going at subsonic speed, you're gonna hear a higher frequency. But whenever a certain object actually crosses the sound barrier means it goes from subsonic to supersonic, then it actually makes a huge cracking sound, like explosion kind of sound, because all of those energies get concentrated and get released to the person's ear at the same time, and that can hear really nice. People who are using headphones, be careful.
There it is.
Did you see that momentary cloud generation, conical cloud generation around that plane? Anyone?
Yes, sir.
That is the instant, or that is the small gap of duration of time within which the plane was actually going from subsonic into supersonic. The high amount of compression and the fluid dynamics of the cloud within that part actually makes a temporary condensation of the water vapor, and that appears to be in that format. Whenever the vehicle goes supersonic, then the whole effect is lost. So sorry, whenever it is above supersonic, then it's lost. That cloud generates really close to the value of supersonic. So let's say for a very small window, let's say 98% to 102%, something like that. I'm not exactly sure for the value, but it happens for a very small range of velocity of the plane that is close to the speed of the sound. I'm not getting actually a very beautiful crash kind of sound.
A sound what we're exploring.
People are not hearing any sound whatsoever. So have a look. This pilot is approaching the aircraft, and you'll see that whenever it is viewed from the aircraft, these people are not hearing any sound, but the sound is coming towards them. The reason they are not hearing any sound, because the sound is not reaching towards them at a speed of sound, let's say about 340 meters per second. It will take some time for the sound to reach up to them. But the source is also coming to them at the same speed. So whenever they are practically receiving that sound that the source is being produced, because the source is also moving pretty much at the same speed of the sound, they are gonna get a large burst of sound, of accumulated sounds. I'm using the term accumulated sound, that's not a scientific term, but I want you to understand that other than experiencing all of those individual crests and troughs or individual compressions and rarefactions of the air medium one by one, these people who are over here, they actually delivered the entire energy of the compressions and the rarefactions in a small package suddenly. And that's what makes the sound so loud whenever the aeroplane actually crosses the sound barrier, because it means that all of those energies that the sound was produced, they are now compressed. So you'll see that if we just allow it to play in maybe a slightly slow motion, maybe let's say 0.25 speed, you'll see no sound is being heard as the plane is coming. It's the regular speed of the sound of the upper wave. Then you hear a sudden out. Do you hear the bang? So that's the sonic boom. So I can pull it a little bit back. It's actually not working at the low speed as I expected it to. So, but have a look. Regular music. Do you hear that bomb kind of like or gunshot type of sound? From this sector. That's the sonic boom. I think we can have it in some other examples as well.
ওটার পিছনে তাহলে কি ওই ক্লাউড কন্ডেনসেশন টাইপের সনিক বুম হচ্ছে?
So is their sound. What the pilots are specialized at, or they are very good at, is that they can control their acceleration to produce the sonic boom after a certain distance. So they can actually make the sound as loud as possible, close to the people that they want to make it at, which is pretty amazing. But it's very important for a certain vehicle or to be structurally strong to be able to that high concentration of sound pressure. It's actually a lot of energy within a very small space. So it can prove to be pretty dangerous. Anyway, I'll moving on to the explanation, mathematical explanation part for the Doppler effect, which I'm going to show you over here. We have two different formulas for sound and for light. For sound, I'm going to define some variables over here. First, I'm going to let me write this formula. So this is the part that I like. So here, what I'm trying to show you is that F is the original frequency or frequency of source. V is the speed of sound in still air. VO is the speed of observer in applicable case, and Vs is the speed of source in applicable case. You might see that I have given a reverse plus minus sign. This is actually minus plus sign over here. Why have I given it like this? What is happening? There are multiple different logics that you can apply to this formula. So F prime and sorry, I didn't label F prime. F prime is the observed frequency, which is the change frequency, observed / changed frequency. one thing you need to understand that because of the Doppler effect, the original frequency of the source does not undergo any change. Source keep on producing the same frequency sound with the same exact frequency. The observer perceives a different frequency because of the relative motion. So you have to be very careful in your choice of words when we are trying to define a Doppler effect. If you ever imply that because of the relative motion between the two things, source and observer, the actual source starts to make a different frequency sound, then you will be entirely mistaken. The source keep on producing the same sound as it was, but what the person experiences gets become different because of the relative speed. So it's not the same thing as the source making a different sound. So be careful about your choice of words. So this is change frequency. So how do we apply this formula? This is very simple. Have a look at this whole fraction. This fraction is our key. One thing that you just have to remember that if they are getting closer, then frequency increases. If they're getting farther by any mechanism, because there are two possible ways: either the source stationary, the observer getting farther, walking away from the source, or the observer is stationary and the source is moving away from the observer. You can have it in either way, or maybe in simultaneous way as well. So if the two things are getting farther, the distance increases, then frequency decreases. So what I need to understand, this f is the frequency of the source. Let's say for our animation, the simulation that we've seen, let's assume that this is the frequency that we are going to observe. This is a ratio that is going to control the variation of the frequency, and this is the original frequency of the source. Let's say this is 100. So this number is going to multiply by something that will be produced from this fraction, which will be the new frequency. So basically, this fraction will control what this is going to be, because this is basically fixed. This is the frequency of the source. It is not going to undergo any change over the duration of the observation. So you have to choose exactly what happens within this fraction by basic logic. So what I'm trying to tell you is something like this. Let's say the speed of sound in still air is 340 meters per second. This is around 25 degrees Celsius. We have about 340 meters per second. Right here at 5. 340 meters per second. Let's say this is the scenario. In scenario 1, let's say the observer is getting closer to the source. Let's say the question tells you that the observer is getting closer to the source at, let's say, 20 meters per second. Now here's the deal. It is a stationary source, so the source doesn't have any velocity. So on the lower side, we're gonna have 340 minus plus 0. So because the source is not moving, so it is 0. Or alternately, I could simply decide not to write this at all. I told you a bit earlier that now the observer is moving towards the source. If the observer is moving towards the source, then this observed frequency is supposed to be bigger than 100, which means this fraction has to be bigger than 1, which means the numerator is supposed to be bigger than the denominator. So what do? You simply add up that speed on the top. So you add 240 plus 20 meters per second. That gives you a much bigger fraction compared to 1. And eventually that gives you the new frequency observed, which can be something you can calculate this. 360 by 340, 100 কত হয়? We get 105.9. In 3SF it's 106. So let me just write 106 hertz. So that's the new frequency that the observer is going to experience if the observer is moving towards a stationary source at 20 meters per second. So this is the effect. So the speed effect of the observer is placed on the numerator side, and the speed effect of the source is placed on the denominator side. How this formula came into existence is not discussed in your syllabus. This actually came through the Huygens propagation theory, and then it actually came into this shape. So because how did this formula came into existence? This is not a part of your syllabus. So I'm not going to show you the derivation of this formula. Just take my word. This is how the formula works. The effect of the observer speed goes on the numerator side. The effect of the source speed goes on the denominator side. The reason I've given the minus sign over here is to give a reverse idea. Reverse idea means if the source is getting closer, try to understand. In this let's say example number 1. Let's say in example number 2, it says the speed of the sound is still 340 meters per second. Let's say the observer is stationary and the source is getting closer to the observer at, let's say, 25 meter per second. Let's give us a different value. So what would be the observed frequency of for the source? Now, so now the source is moving closer to the observer. Now here's the deal. Closer means frequency should increase. So if I just write the formula over here, f prime equals to something, this is the fraction that we're going to deal with, into 100, we're expecting this frequency to become increased. So now the observer is stationary, so we're not going to write anything, add or subtract anything on the top side, so the top side becomes 340 itself. But this whole fraction is supposed to be bigger than 1 because you are expecting a frequency increase because the distance between them is decreasing. The question said that the source is approaching towards the observer. So numerator is same, but the denominator has to become smaller so that the ratio value of this fraction is more than 1. So this is going to become 340 minus 25. So the reason I have written this in minus format is that if the distances are closing in, then you use the plus over here or use the minus over here so that the fraction value is more than 1. If the distance value is, if they are getting further away from each other, then this fraction needs to be smaller than 1. In that case, you either make the denominator small, so you either make the numerator small, or you can make the denominator big. So this is the idea for this two reverse correction. So if you can remember this information, you can very easily determine what's going to happen to this fraction for all this calculation and so on and so forth. And this will essentially give you some value, which I can calculate actually. 340 divided by 325, 25 or 15? 15. We get 108 hertz. So that's the basic calculation format. For two different type of scenario, we have two different things. And if it so happens that in some specific type of math, both of them are moving. Let's say if both of them are moving, there are two different things that you can do. One is that you can consider one of them to be stationary and apply the whole formula for the other one. For example, if a certain scenario tells you like this, let's say here is a scenario, there is the source, and here is the observer. So let me make the source by a loudspeaker. If the question tells you something like this, that both of them are moving. So let's say the source is moving in this direction at, let's say, 10 meter per second, and the observer is moving in this direction at, let's say, 20 meter per second. Now you have to apply for idea. The source is trying to get away from the observer is approaching towards the source. So the speed of the source is going to be responsible to reduce the frequency. The speed of the observer is going to be responsible to increase the frequency. So you add the observer speed on the top, and you also add the source speed at the bottom, because this is trying to reduce the observed frequency because it is trying to increase the distance. This is trying to decrease the distance. If this discussion becomes difficult for you to understand, then be my guest. Just don't do it. Have a look at this whole scenario and find out the relative speed. What is the relative speed between the source and the observer for this scenario? I mean, if you
10
consider
meters
one of them is stationary, the relative speed between them is 10 meter per second. Use the 10 meter per second, considering the source is stationary, apply the 10 meter per second for the observer speed on the numerator side, not preferably on the denominator side, because here both of them are moving and we are considering the source to be stationary and assuming that the observer is getting closer to the source at a speed of 10 meter per second. So you're going to get pretty much the same answer. And all of these answers will match perfectly for your requirement. So this is actually pretty unlikely for your CA question pattern. I have rarely seen this thing, but if it so happens, you find the relative speed, use it at the observer speed, and it's gonna perfectly work out. Vice versa, if the situation was like that, this thing is going at 10 meter per second, let's say in another scenario, if they gave us that, let me write that with blue, that the source of the speed of the observer was not 20 meter per second, let's say it was 5 meter per second. In this case, you have to understand that over the duration, the distance between each other is actually increasing. So practically the observer is falling behind. So this is a scenario as if the observer is stationary. We are considering the smaller, low speed object to be stationary, and the source is slowly getting further away. Every second, the source is getting 5 meters away from the observer. So we can place that thing as a source getting further away. So negative information. So a positive addition at the bottom for our calculation. So there is quite a lot of practice for this type of equation to be used on. So you can actually try that up over here. And it will be pretty simple for you to try out. If you can, I'll help you for that questions as well. This is the part for the sound where we have two different variations over here. There is another different formula for light. If you wonder why do we have a different formula for light, because the speed of light c measured to be about 3 into 10 to the power 8 meter per second, it happens to be an universal constant. In vacuum, every electromagnetic wave has this speed. And Einstein's special theory of relativity actually teaches us, and it is actually experimentally proved as well, that different people moving at different speeds, even at considerable fraction of speed of light, if they try to measure the speed of light, they will still be measuring the speed of light to the speed of light. So I'm not gonna get into the detailed explanation why the theory predicts this and how it was proved, but I'm gonna tell you what it actually offers. There's a reason why I'm bringing you to the idea of relativity. The idea is like this. Let's say there is a light source and there is a stationary observer beside the light source. By some mechanism, he measures the speed of light to be c. Basic Newtonian mechanics tells us, if in another scenario, if it so happens that there is a light source and light is coming out of the stationary source at the speed of c, and if this observer is moving toward in the same direction as the light speed at let's say c by 4 as quarter of the speed of light, if it is possible, and he still measured the speed of light, logic tells us that he will measure the speed of light to be c minus c by 4. This is the idea of basic mechanism, because light is going this direction c, he is moving at c by 4, so he's gonna try to measure the relative speed. So he's gonna measure, let's say, 3/4 of c, or vice versa. If it's the other way around, let's say the source is shooting light at c and the observer is moving in opposite direction at c by 4, because so now he should be measuring the speed of light should be c plus c by 4. This is what basic Newtonian mechanics or typical physics that we have come across actually proposes, the idea of relative speed. What Einstein's special theory of relativity says, no matter, irrespective of the speed of the observer, for all of his motion, irrespective of the speed of the observer, he is going to always measure the speed of light to be exactly c. That's the statement for special theory of relativity. Why it happens, how does that happen, how did Albert Einstein came up with this idea, how it was proved, and how it was actually experimentally measured and proven to be true. I'm not getting into that detail, but this is the content. There is a reason why I'm telling you this, because the speed of light is not considered to be a variable, whereas in this case the speed of sound could be measured and varied with respect to multiple factors, and which is definitely smaller, far too smaller compared to the speed of light. That's why we do not have the exact similar formula for the Doppler effect of light. You don't have to know this reason. I'm showing you this reason to give you a bit of a background that why do we have two different formula. The Doppler effect formula for light is actually pretty small. The observed observed difference in frequency delta f, if it is given by delta v divided by c into original frequency, and then the change frequency depending upon whether the objects are getting closer or farther away, doesn't matter, would be given by plus minus delta f. Let me give you a bit of an idea for what this means. Let me give you a bit of an idea. Let's say a star, a distant star, is giving us a light of, let's say, a distant star is giving us a wavelength of, let's say, 470 nanometer. So the frequency of that star should be 10 to the power 8 divided by 470 10 to the power minus 9. So how much frequency do you get? বলো man, help করো।
Sir, second.
6.38.
6.382 into 10 to the power 14.
So okay, let's say a distant star is emitting light at this frequency. If this star, I'm saying a distant star, so it might be as well on the other part of the galaxy, it might as well be the other part of the nebula that we are at. So if the star is moving at a significant speed away from us, we'd still be able to observe the Doppler effect. So let's say this star is moving away from us. I'm highlighting this word away because this will be a very important word for us in the later part of the problem. Let's say this star is moving away from us at a speed of, let's say, 10% speed of light. 10% speed of light means the radial speed between us and the star, delta V, is 10% of speed of light, which is basically 0.1 c. Now, the important bit works is that the difference in observed frequency should be delta V, which is 0.1 c divided by c into that observed frequency, that is 6.38 into 10 to the power 14 hertz. So you're going to get some value. Actually, I can see that cc crosses out. So there would be 1 decrease of the power. So I can write 6.38 into 10 to the power 13 hertz. That will be the difference in frequency observed. Now, because I said this distant star is getting away from us, so the observed frequency will be smaller. So how much smaller? So the new frequency that we're going to see, let's say f prime, the different frequency, this is going to be 6.38 into 10 to the power 14, the original frequency, minus the change frequency that we have seen. So that is 6.38 into 10 to the power 13. Because we are sitting away, that's why we're subtracting. If it was getting closer, then we would be adding. Getting closer means observed frequency higher. Getting farther away means observed frequency is lower. So if we do that calculation, how much do we get? We get 5.74.
So 5.746 into 10 to the power 14.
Did you get 746 over here?
So एक बार देखे नहीं sir.
दाঁড়াও।
No sir, 742.
This should be 5.74. It's okay.
Yes, sir.
This is good. 10 to the power 14 hertz. So this will be the observed frequency from us. So এই হচ্ছে লাইটের জন্য করার formula. So you have to first find out the change of frequency that we're going to observe, and depending upon whether the two objects are getting closer or two objects are getting further away, you have to find out the observed frequency with a second set of formula. So take a look at the difference of these two formula. I'm going to zoom out, and so that you can have a look at the difference of these two formula. So the first formula that we have given over here is applicable for the sound, where we have both the effect of the observer and the source movement with respect to the speed of the original wave of the medium, sound in this case, affecting within the same fraction. And you can find out the observed frequency in a single step. Whereas for light, the formula is different. We have to first find out the change of frequency that we're going to observe, which is going to come as a fraction of this thing. I mean, if you wonder that why does this formula come from, this is actually pretty simple. I mean, what they are using over here, because have a look, c equals to f lambda, right?
Yeah.
No, I'm not saying how this was got derived. What they actually did is that delta f by f should be equal to delta v by c. So they used a sort of a proportionality for that. This difference causing this much variation. This original frequency is the speed of light. So something like that. You don't have to remember that. Forget about that. So if you don't want to, you don't have to. But what I wanted you to see is that change of frequency is measured as a fraction of speed of light multiplied by the original frequency of the light. So that's how we find out the difference. And depending upon whether the two objects are approaching each other or getting further from each other, you do the addition or subtraction respectively. এই পর্যন্ত বুঝা গেছে কিনা বলবান দেখো
Yes, sir.
Yes, sir.
ঠিক আছে any question anyone else apparently no this behavior is basically the reason that we can talk about the ever expanding universe. So what happened, I mean the basis for Hubble observation was that, let's say we have observed a certain star in the night sky. Let's say this is the night sky, this is the earth, there is a distant star, figure not down to scale. Let's say in the year 1950 we observed this star by observing the constellation was emitting a frequency of, let's say, 200 hertz. I'm just giving some numbers to make sense with you, not going with the 10's power and everything. What was found out, as we observed and recorded their individual frequency of light emitted, if we did the experiment multiple times, in 1990, we found that this frequency is now, let's say, 160 hertz. And this behavior of reduction frequency was not exclusive for a star. This was applicable for pretty much all the stars that we have observed. For some of them, this reduction was more. For some of them, this reduction was less. What this gives us an idea that this 200 hertz of frequency of light that we have observed for this star to get out at 1950, it was not its original frequency. Neither is this. The reason we are defining them to be not their original frequency, because whenever we have a decrease of the original frequency, it means that now this object is getting away from us at a further speed compared to at what speed it was getting away from us from here. So a reduction of observed frequency means what? A reduction of observed frequency means, first of all, that the two objects are getting further away from each other. The two objects are getting further away from each other. That's the first thing. Because reduction frequency means that you have to do the subtraction. From this formula, you have to do the subtraction. And this delta V was seen. This delta V is basically tells you that how much speed variation did it undergo. How much speed variation did this thing undergo? So that variation of, let's say, 40 hertz that I have given over here for as an example, this corresponds that how much faster is it getting away from us after this 40 years. So maybe in this case, maybe I'm just giving you some idea. In this case, this star was getting away from us at, let's say, 1 million kilometer per second. Assuming that the relative speed from Earth to that star was 1 million kilometer per second. Now, this is definitely higher than that. So this should be 1 million plus something else. I don't know how much that is. That's a question of calculation. This many kilometers per second. Because this is now getting away from us at a much higher speed, we are now observing it to emit us a light at a much lower frequency. Now, if you wonder, couldn't other stuffs happen, like celestial things, that the star has gone under sort of supernova stuffs? I mean, other celestial happening that could give rise to this decrease. Well, individual celestial happenings can happen to one or two stars, or what a few of the stars that we observe in the whole constellation of the night sky. This should not be applicable for the entire constellation. But what was found out that observing figures from the Hubble telescope, what we human beings could decide that this behavior of decreasing frequency observation over a duration of time, significantly long duration of time, is applicable for nearly all the distant stars. Some of them undergo a much higher deflection, higher decrease, some of them undergo a lower decrease, but it is in generally applicable for everyone. Basically, from that idea, from this mathematical observation, Stephen Hawking came to the idea that universe is expanding, and it is expanding, stars are getting away from us, and they are getting away from us in a way that they are speeding up and getting away from us. So they are, I mean, the farther the objects are, the faster they are moving away from us. And this behavior of the current observed frequency having a lower frequency is what we call the redshift. Redshift means the same star that appeared to be bluish, let's say 40 years earlier, might as well appear to be yellowish right now or greenish right now. Or maybe the same star that appeared to be yellowish, let's say a couple of decades earlier, might appear to be orange or slightly red right now, which means their observed color is slowly moved to the lower frequency side of our visible spectrum. So that same star appearing to have become more red. It's not essentially red. It means its observed frequency has slightly shifted towards the red region of the visible spectrum. That's what we call redshift. Vice versa, if the opposite thing could be observed, which is not physically observed in the visible universe, this could be said to be blue shift. Now, blue shift is not visible for us for a lot of reasons, because the stars in the universe actually don't work that way. But a small example for blue shift can be work whenever we observe the exact color of Mercury. Mercury is the closest planet near the sun, which has extremely tremendous high speed. And when the Mercury goes around the sun pretty fast, for certain observations, it was found that Mercury can give us two very different colors compared to its original color. Now, how did they measure the original color, and how did they measure these other stuff? I mean, what is the technological breakthroughs, I must use plural, that they had to overcome to be able to measure these stuffs to acceptable range of uncertainty? And this is a very important word, acceptable range of uncertainty. I mean, you observe a star that is billions of miles away from us, and you measure its intensity and its super wavelength, and that should not be affected by the atmospheric dispersion, or that shouldn't be affected by the other stuffs and the whole earthly environment. And you need to express that data within a certain percentage uncertainty, which should be acceptable. So how much precision and yet powerful equipments are we talking about to be able to do that kind of observation in the first place and be able to handle that data processing as well is something. So it's something. It's not as easy as it sounds. That's the thing that I can tell you. But it's very difficult. It's very difficult. But as time is going by, our capabilities are increasing as well. So that's a very important thing. So that's pretty much it for this idea. Here we have idea of the Doppler shift over here. So we have a scenario. We have some MCQ questions over here. We have some paper 2 questions over here. আচ্ছা, এখানে যে আনসারগুলি দেওয়া আছে সবগুলি আনসার তোমাদের সাথে পারফেক্টলি ম্যাচ নাও করতে পারে, because they have used a different value for this thing. আচ্ছা, এখানে আমি I actually copied this sheet from the net, and then I found this good amount of practice. এখানে তো এই ওয়ার্কশিটটা করার জন্য তোমাদের একটা প্রাইমারি জিনিস জানা থাকতে হবে, জাস্ট এক্সক্লুসিভলি এই ওয়ার্কশিটের জন্য, বাট ইটস নট ইনক্লুডেড ইন ইওর সিলেবাস। সেটা হচ্ছে যে at 0 degrees Celsius temperature, the speed of sound in air is 334 meters per second at 0 degrees Celsius. And then for each 1 degree Celsius increase, you have a 0.6 meter per second increase of temperature. So increase in speed of sound. মানে হচ্ছে if we're trying to find out the speed of sound at, let's say, room temperature 25 degrees Celsius, the speed of sound at 25 degrees Celsius should be 334 plus 0.6 into 25. How much do you get from here? দেখো তো।
359.6. 349.
We get easily 349.
Yes, sir.
So 349 or maybe equivalent to 350. If you go for 2SF value, 350 meter per second. So in cases where the question tells you the exact temperature, you can actually you will be able to calculate the speed of sound with this formula, that this is the amount of increase meter per second per degree Celsius, and this is the amount of increase from 0 degrees Celsius. If nothing is mentioned, you can directly use 350, assuming it's the room temperature. If 0 degrees Celsius is mentioned, you have to use the speed of sound as 334. There is a solution that is also attached, which is not added to this PDF. I have to look up the solution, but in the printout that I'm giving you, that has a solution in the back of it, which was made by one of our students. You can look into this as well. Nothing is above mistake, so that solution might also have some mistake. I would like to have your eyes peeled. Use your logic and don't take the solution as a what can I say, as a wishy-washy, like divine words. So attend those worksheets and you can solve them pretty easily. That volume of worksheet actually have everything, pretty much like the way you have your first booklet arranged. So there will be note first, then there will be MCQ compilation, then the mark scheme, then the paper 2. That's how one chapter will be compiled. I mean, this whole thing would be there. This entire worksheet that we're seeing over here, this whole thing would be here. And you can also read about the Doppler effects from the textbook that you have, whether the Cambridge textbook or the Mike Randall book. Either of them is very well written for Doppler effect. The idea is pretty simple. You can have a lot of videos and animations going around. So that is also pretty helpful. So Doppler effect থেকে আর কিছু পড়ানোর নাই. Actually, we can try some problems from here. I can help you with some of these problems. Can we try number 1? Give these questions a try. I'll help you. First, find out the speed of sound using the 22 degrees Celsius information, because your speed of sound would be different, and then go ahead to do the problem. For your syllabus, you don't have to do that speed calculation first, because it will be given to you directly. But to solve this piece of paper that I found out in from the internet, is that you need to know that relationship. Otherwise, it would be at difficulty to calculate the speed of sound. That's why I give you this additional formula. Not needed for your syllabus, but additional knowledge cannot harm you. Or can it? My goodness. Pulwan, তোমরা এই প্রবলেমগুলো একটু ট্রাই করো কয়েকটা। If you're done with number one, go ahead forward. I'll help you. I'll be right.
Sir.
হ্যাঁ ফায়াজ কি যেন বলতেছিলা বলো। These questions are very nice. আচ্ছা শোনো, I would like to discuss something else from the superposition worksheet rather than giving you time for this. You can try this at your own time, and if some answer doesn't match, we can look it up later in the classroom discussion. আমি তোমাদের সুপারপজিশন ওয়ার্কশিট থেকে ফার্দার কিছু কোশ্চেন আলাপ করাই, মানে তোমাদের লাগবে। আমরা পেপার 2 করতেছিলাম মনে হয় সুপারপজিশনে। Did you start this paper? I think we did because I discussed the number 5 problem last class. This one. Remember this?
Sir,
We discussed this one as well. Acha. This is another question that I'd like to discuss. This is a very unique one. The reason I call it unique because of the setup. What you can see over here that we are using a diffraction grating. Light of a laser light of wavelength 632 nanometer is shine to the diffusion grating, it is going to produce a circular pattern. But other than having a circular screen, for this exclusive question, we have used a flat screen. And linear dimensions are given to us over here. From this linear dimension, you have to find out the angle theta, which have to be used further on to calculate the further problem, which means d sine theta equals to n lambda 459. You have to, to be able to apply the formula d sine theta equals to n lambda, you have to hello, okay, so you have to find out the theta from here. But interesting information that each of the theta 1 or theta 2 for the first maxima, second maxima, so on and so forth, are measured from the central maxima to that position, which means if you consider this thing as a right angle triangle, either the top one or the bottom one, this side xp would be half of that, and this is the adjacent and this is the opposite. So you can use these two information by tan theta proportion to calculate the angle over here. Don't use the whole thing, because you're not going to use the whole thing, because we are trying to find out half this angle. We're trying to find out this angle, not all of it. So that's important information. So for this problem, you have to first find out the theta value using some small bit of trigonometry, and then you can directly go ahead and apply the whole formula once again, and you can get the whole idea. আচ্ছা, এই ফিগারগুলো আমরা কিভাবে আঁকবো সেটা আমি তোমাদেরকে দেখাই। Performance sensor honestly that's showing figure 5.1. I think this was also in one of the questions from the first question as well, actually this one. Yeah, এটা দেখালে তোমরা বাকিগুলো খুব ইজিলি আঁকতে পারবে। There are many different acceptable answers for this, but there is one specific version that I personally like. What I'm about to show you is what I like better. So you can follow that, or you can follow steps by the way your textbooks recommend you. It's all right, but I'm going to show you the version that I like better. The way you can see over here, the gaps between these two wavefronts, which means the wavelength is nearly equal to the gap size. It's nearly equal. It doesn't have to be exactly equal. It's nearly equal, which means this will give us circular wavefronts with a really wide angle. So what I'm going to do, I'm going to use my compass. I'm going to first find out the approximate midpoint of this hole. You can eyeball this, or you can use a ruler to find this out. Find out that point, midpoint. Place your compass over here. So what you're going to do right here, you're going to place your compass over here. Take this much radius. Don't draw this line. Just measure this much from the center of this thing to the thing, and draw your first wavefront. Let's say like that. Then measure, keep your compass pin over here, measure the whole thing. This is a double 2 wavelength. Draw a second one. Leave a small, this is not perfect, this should be a bit more wider over here. Leave a small slice of space left on the two sides. Or if you want, you can actually make it touch over here as well. Because you can, if you want, you can make them touch over here as well. And then a third one. Drawing at least 3 is essential to show the diffraction grating, because whenever you have drawn at least 3 wavefronts, you can impose the idea of wavelength remaining same. But if you only draw 2, you are showing only 1 wavelength, so there is no way to compare the wavelengths. So that's the behavior for single wave, which is very simple to draw, in my opinion. For this scenario, where the gap size is significantly bigger compared to the wavelength gap, did I show you this drawing before?
Sir.
Did you say yes or no?
Yes, sir.
আচ্ছা, তাহলে তোমরা জানো why am I wasting time in this? So you draw flat lines of the same size, then you from the side you draw the curves, so you know the stuffs. Acha, I actually forgot, then it suddenly popped in my head that I did show you these graphs. Sorry, my bad.
স্ট্রেট লাইন গুলো কি ব্যারিয়ারের মানে এন্ডের সাথে প্যারালাল হবে?
হ্যাঁ, some similar questions. তোমাদেরকে আমি আরেকটা ইম্পর্টেন্ট ফিগার দেখাবো একটু পরে, দাঁড়াও। স্টেশনারি ওয়েভের একটা ইন্টারেস্টিং ফিগার আছে যেটা বোঝা দরকার আছে। These questions that I'm going through, they are pretty much the same stuff, so that's why I'm not actually taking much time to read through them. This is actually one of those difficult questions to answer in my brain. Describe to determine the wavelength of a sound on air using stationary waves. You include a diagram of the apparatus in your answer. So this is basically they're asking you to give the resonance tube figure, which is the typical experiment that we go for. To draw the figure, explain how this experiment is done, and blah blah blah. This is a nice figure. আচ্ছা, এই গ্রাফটা একটু ভালো করে খেয়াল করুন। It's a nice question. Have a look at this question. The variation in distance x of the intensity I of a stationary sound wave is shown in figure 6.1. So I slash arbitrary units. They've given arbitrary units, meaning that this could be kilowatt per meter square, this could be watt per meter square, milliwatt per meter square, this could be anything. Because intensity is given by power over area. So watt per meter square. So from this figure, which of the points would you define as nodes and which of the points would you define as antinodes? Take a good look, try to use some ideas, and I'll help you in a bit. But I want you to try first. This is intensity versus distance. Which of the points are supposed to be nodes, which are supposed to be antinodes?
আমরা কি অ্যামপ্লিটিউডের জায়গায় ডিসপ্লেসমেন্টকে কনসিডার করব?
হ্যাঁ বলো। এখানে নোড হবে কোন পয়েন্টগুলো আর অ্যান্টিনোড হবে কোন পয়েন্টগুলো?
আমরা কি ডিসপ্লেসমেন্ট কনসিডার করব অ্যামপ্লিটিউডের জায়গায়?
Maximum displacement is the amplitude. Along the stationary wave, all the points would have some displacement. All the points would have different amplitudes. The point which have the highest amplitude would be the loudest. So how do you label N and A? Let me elaborate to you what I'm trying to tell you over here. The most common problem that students who do not observe this graph carefully is that in some cases they label this point as an antinode, which is correct, and label this point as a node. Because if you consider the shape of a stationary wave shape practically looks like this. And then do we have the opposite side as well? This is applicable, this is actually a mistake. This is correct anyway, because this is my highest intensity means it is the loudest point. This is not the node because this is not the x-axis. You have to look that on this arbitrary unit, this is the x-axis, which means This point represents the silence. As you go further up, you have louder, 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 loudest sound at this level, which means the location where you don't get any sound, those are the nodes, which means this point cannot be node. This is wrong. This point is supposed to be your node. So that's the difference. And এখানে একটা জিনিস বলছে, এই যে আমি এখন যে লেবেলিংটা করলাম, এই লেবেলিং এর জন্য আমাকে 1 মার্ক দিবে না, although I'm pretty correct. I'll tell you why. Read the question. Labeling করতে বলছে কোথায়?
X-axis.
This is good, but this is not good. I was supposed to label here. These two are all right. বুঝাচ্ছে কি বলতেছে?
জি স্যার।
Information matters. Question ভালো করে পড়ে আনসার করতে হবে, প্রশ্ন না পড়লে বিপদ আছে। সো এখান থেকে আমরা অ্যান্টিনোড এবং নোড লেবেল করলাম, এরপর কোশ্চেনটা আরেকটু ফার্দার আছে, দেখি। The speed of sound in air is 340 meter per second. Use figure 6.1 to determine the frequency of the sound wave. এখন তোমরা জিনিস দেখো, this is a graph in the centimeter scale. এখানে আমরা অ্যান্টিনোড থেকে নোড পর্যন্ত কতটুকু স্পেস পাইলাম, or alternately you could directly calculate যে নোড থেকে নোড পর্যন্ত কতটুকু আছে, because we know that from one node to another node হচ্ছে half lambda. This is half lambda. Or you can also say that from one antinode to the next node হচ্ছে quarter of a lambda. So you could either measure this much, or you could measure from node to node. Anyway, so measure one of these stuffs by observing the horizontal axis, and you tell me how much your lambda is from the figure. Try this. Take a very good look at the scale of this figure. You can see over here that 20 divisions on the horizontal scale is represented by 20 centimeters. So each small division shows you 1 centimeter. So the scale is actually pretty simple to work with. So how much is your lambda?
$17 centimeters.
70?
Sorry, 34 centimeters.
34 centimeter is not your lambda. 34 centimeter is your lambda by 2. This is a node. This is another node. So node to node distance is 34 centimeter. That is lambda by 2. So lambda should be how much? Double of that.
68 centimeters.
68 centimeter. এই জিনিসটা কি সবাই বুঝতেছো কেন এটা 68 সেন্টিমিটার হইতেছে? বলবা না, এই জিনিসটা খেয়াল করো। This is a unique graph. This is not very common graph, but I want you to understand what is going on in this graph. কেন এটা 68 সেন্টিমিটার হইতেছে এটা কি বুঝতেছো?
জি স্যার।
So be careful. Node to node distance 34 centimeter, or you can say that from node to antinode or antinode to node distance was 70 centimeter. Either you multiply the 70 centimeter by 4 if you use this one, or you multiply the lambda by 2 by 2 if you use the node to node or antinode to antinode. You can work either way, but whatever you do, be careful for that. So you get the lambda from here, from the graph. Once you get the lambda, the rest of the part is pretty simple. B equals to f lambda gives you the frequency of the sound. That's just simple. In terms of lambda, how many wavelengths are here for this stationary wave formation?
3/4 lambda.
Beautiful. Zarif is correct. But does everyone else see 3/4 lambda here? ঠিক আছে, এটা জিজ্ঞেস করছি এই জন্য কারণ হচ্ছে যে এখানে লেংথ তো টিপ ক্যালকুলেট করতে বলছে। সো তখন ফ্রিকোয়েন্সি দেওয়া আছে, স্পিড দেওয়া আছে, তুমি ল্যাম্ডা বের করবে, তারপর সেটাকে 3/4 দিয়ে মাল্টিপ্লাই করতে হবে। দ্যাট বেসিক্যালি ডাজ দ্য জব। আচ্ছা, আমি কিছু স্পেসিফিক প্রবলেম দেখাতে চাইছিলাম, সেই প্রবলেমগুলো কোথায় আছে আমার আগে বাই করতে হবে। একটু ওয়েট করো,